Chapter 2. Physical Field Theories. By R.J. Rummel. There are two worlds, the world that we can measure with line and rule, and the world that we feel with our hearts and imagination. Leigh Hunt, Men, Women and Books. This book will present a psychological ontology of human beings, who will be pictured as a basis, source, and focus of a whole, a field integrating their intentions and their biological, ecological, psychological, and social-cultural natures. The most important concept within this perspective is that of a field, a concept unfortunately diversely employed in the literature and denoting different conceptions of humankind. Throughout this book my approach will be to develop gradually a feeling for a field conception, perspective, and framework. The purpose of these introductory chapters is to orient and ground this feeling by describing physical field theories and then a variety of psychological and social field conceptions. This excursion into the fields of nature and humanity is not without some danger of misunderstanding, however. By beginning with physical field theories, I may imply that our intentional field to be described in this book is simply an analytical model, a copy of physical field theories applied to humankind. And I may confirm this impression by describing the social and psychological field theories of Brown, Couchot, and Gestalt psychology, which were explicitly and self-consciously such copies. Let me say at the outset, therefore, that physical field theories are not precursors or models of our intentional field, but are simply theories sharing certain basic similarities with this field. I am not suggesting, as does Lundberg, one for example, that here are physical field theories which have been wondrously successful, and because we want to be similarly successful, the intentional field therefore models them. Rather, all I intend here is to enhance our understanding of the intentional field by briefly considering these physical ones. 2.1 Action at a distance. A good way to introduce physical fields is by way of action at a distance, a problem that has historically puzzled philosophers and scientists and that has played a significant metaphysical role in the growth of scientific knowledge in field theories. 3 Some discussion of attempts to understand this problem provides us with a helpful entree into the fields of nature and casts some first light on our intentional field. To begin by exemplifying the problem, consider this simple question: how does the moon affect the tides? By the moon's gravity? Of course, but how is gravity transmitted from the moon to the earth? The 239,000 miles separating them make it difficult for the moon to bump the tides along. Moreover, in the relative vacuum between the moon and earth, we find no clearly identifiable medium to transmit gravity. How then can the moon cause effects on earth at a distance? How can there be such action at a distance? As a related puzzle, consider magnetic attraction, specifically the familiar pull of a magnet across space on a nearby metal bar. This attraction occurs whether magnet and bar are in a vacuum or not. How can this action at a distance be explained? Clearly, our answers will depend on our perspective, on our theories of reality, of matter, action, and distance. These theories should tell us whether action at a distance is conducted through a medium or not, and if a medium is theoretically necessary, its nature must be explained. Early Greek philosophy had essentially 3 such answers to the riddle of action at a distance, which troubled them no less than it does our contemporaries, when we stop to think about it. First, there was Plato's perspective that things moved relative to each other either because of their nature, some inherent force, what we now might call energy, or because of mutual attraction. In other words, action at a distance occurred because things either had a natural tendency to so behave, thus denying effects as being caused at a distance, or because like attracted like. Water was attracted to water, fire to fire, earth to earth, and so on. The atomist had a quite different view of reality as propounded by Leucippus and Democritus, which was either atoms in motion or void. In this framework action at a distance was inconceivable and could occur only as a chain of contacts between atoms. This is the classic materialist answer: action at a distance occurs by material propagation. As a common-sense solution, this answer has satisfied many. Even Aristotle, although differing in worldview from the atomist, had made a substance basic to all things from which force could not be divorced, and thus had offered the same answer as the atomists. Action at a distance had to be materially propagated, it had to be a material push or pull. 4. The third perspective was occult, putting faith in supernatural powers and explanations. In this view, action at a distance was due to some prime mover, some divine intelligence or gods of nature. This occult view came to dominate during the Middle Ages, when the apparent action at a distance observed among heavenly bodies was explained by angels or God's hand. In a variety of manifestations, these three perspectives on action at a distance have been continuous threads in the philosophical scientific debates on the problem, extending down to the present day. A brief sketch of this historical debate since the early Greeks will be useful, especially in contrast to a modern, positivistic twist. Now, Plato believed action at a distance was a sympathetic attraction between material things. The atomists and Aristotle saw action as only a physical push or pull, and some assumed divine or supernatural forces. The Stoa of the later Greek period, from 200 BC, accepted a variant of Plato's view which later highly influenced the Romans. For example, Posidonius, a chief Stoic philosopher, held that sympathy united all things in the universe and that permeating the world and pervading space were forces emanating from the sun, of which tides were then simply a manifestation. Action at a distance was due to forces linking two objects, a sympathetic union brought about by mutual action. Although this view influenced the Alexandria school, especially the Neoplatonist Plotinus and Cicero, it had little impact on Christian European thought except to promote astrology, and would not bear scientific fruit until the 17th century. In transition to this century, two original thinkers of the Middle Ages should be mentioned. Roger Bacon, 11th century, argued that action at a distance was carried by excitation of a corporeal medium. A sort of chain reaction took place, a multiplication of the qualities, or species, of an object which could be likened to wave action, propagating forces over a distance. Magnetism, then, was spread physically by a wave of contiguous contact processes. 6. By contrast, William of Ockham, 13th century, accepted neither Aristotle's push-pull view nor Bacon's explanation of action at a distance. In what was a radical position for the time, he altogether accepted action at a distance without the necessity of mutual contact. He believed a simultas virtuosus sufficient for explanation. The intellectually remarkable 17th century saw the beginning of a serious and broad concern with this problem, as with so many others. By then there was a disengagement from theological answers to scientific questions and a new interest in atomism, which during this century flowered into the corpuscular view of action at a distance. One of the most influential of these corpuscular theories, although an odd one to the modern mind, was Descartes' vortices. Descartes believed action at a distance must be explained by either divine powers or some material means of propagation. Taking the latter route, for which there was some experimental evidence, he explained gravity by a vortex, a motion of terrestrial matter toward the center of the Earth, a pressing of things downward. Action was not propagated through distance, but was rather the result of matter in motion, a medium of subtle particles. A contrasting corpuscular view was held by Leibniz, who while believing also that action at a distance was to be explained mechanically, thought such action was caused by mutual contact and release of inherent activity, rather than by a vortex. The ancient and 17th century views on the problem were brought together by Newton. In private, Newton felt that action at a distance without some medium was absurd, but believed there was insufficient scientific evidence for one theory or another. 8. Even though the nature of gravitation was basic to his concept of force, Newton was still reluctant to engage the problem of action at a distance. Instead, he treated gravity as independent of whether transmitted by a medium or not in his scientific work. Even though in private correspondence he endorsed the view that action was transmitted in some kind of subtle ether. 9. In spite of this private view, the success of Newton's system and its intellectual power made force as action at a distance fundamental in Newtonian science. Force became the intervening variable between cause and effect. Soon thereafter, George Berkeley, one of the most probing minds of the 18th century, anticipated modern positivism by arguing that the concept of force is a construct, an invention to link two events. Moreover, he recognized what is still not well understood, that on close inspection the theory of action at a distance by contact or mechanical transmission is as problematical as action at a distance without a medium. How does contact work, and why, for example, do not material things in transmitting causes by contact interpenetrate each other or mix? Does not contact imply that the edges of things are in the same space? But then, how can this be? However, if they are not in the same space, they are separate and must be acting on each other at a distance. During the 19th century, some recognized the midwife role the concept of force played in understanding action at a distance. Others, rather than accept this concept of force, deemed it as metaphysical as the idea of action at a distance without a medium. The philosopher-physicist Mach 10, for example, in his passion to purge science of metaphysical concepts or assumptions, drew a special bead on such forces and tried to extirpate them altogether. Just to bring the story of action at a distance up to date, Einstein's theory of relativity not only overthrew Newtonian physics but also ruled out action at a distance. Now action at a distance without a medium must occur simultaneously. However, the possibility of simultaneity was eliminated in Einstein's theory, because the velocity of light sets an upper limit on the velocity of action at a distance. Moreover, gravitation, around which views on action at a distance have always swirled, is no longer a force in the general theory of relativity, but is itself a property of space-time. 2.2 Action at a distance and the psychological field. Delete what, after all this, is the connection of action at a distance to physical fields and especially mankind's intentional field? In trying to understand the effects of gravitation and magnetism at a distance, force became a stepping stone concept, providing a cognitive link between objects without specifying the physical nature of this link. Now, field became a concept defining the medium surrounding the object through which the force is worked. Field was thus an auxiliary concept for comprehending and defining the operations of forces between bodies at a distance, for example, gravitational fields and magnetic fields. These I will detail in the next section. At this point let me ask whether there is a comparable action at a distance problem in understanding human beings. The answer is yes, and should be understood in this way. The behavioral, stimulus response or reflex, view of humankind is comparable to the mechanistic interpretation of action at a distance. Causes are transmitted by contact, by material propagation. Human action results from mechanical stimuli operating in defined ways, such as by reinforcement and conditioning, or through physical drive states and habit strengths. To understand behavior, then, means to determine the physical events, conditions, and processes comprising and transmitting such stimuli. As the tides were once accounted for by the moon's motion pushing air and creating wind, which in turn pushed water to create tides, war is explained, for example, as being caused by capitalist surpluses that must be sold abroad, creating imperialist expansion, competition, and exploitation. Human action, however, is not the simple result of physical causes being mechanically transmitted as stimuli, as I hope this book will attest. Human beings may be part of an interdependent system, such that any action is the consequence of complex interworking relationships. Moreover, forces may be involved that emerge not from the propagation of stimuli, but from meanings, values, and their own will. A gravitational-like field of subjective forces acting without any consistent material vehicle may hold us in our psycho-socio-cultural orbit. Behaviorists or materialists view our behavior and the structures, aspects, events, and so on of our physical and socio-cultural environment as being distinct, as being separate, as though there were clear boundaries between them all. They then see a need for an explanation to move from structures, events, and so forth across these boundaries to behavior, and the explanation is one of a material connection between things, much as clear discrete material circumstances lead to murder in a cheap mystery novel. Therefore, forces or causes are propagated from a source, such as poverty, or capitalism, or broken families, along a causal chain to produce behavior, crime, war, juvenile delinquency. Another view, and the one I maintain, is that no distinct boundaries separate us and our physical and social-cultural environment. Rather, all are embedded in a medium comprising the unified whole of potentials, dispositions, and powers, and through which forces are manifested. There are no physical causal chains explaining behavior. Rather, there are systems of interdependent forces. Capitalism, poverty, and broken homes have their effects, therefore, only as they are processed, transformed, and modified through such a field. The seat of human behavior lies in action within the field itself. But I am getting ahead of myself. 2.3 Electromagnetic and gravitational fields. Delete physical field theories originated in 18th century physics and were first developed for continuous material media such as fluids and for heat conduction. Some attempt was made to apply such a field approach to gravitation, electricity, and magnetism, for example, by Lagrange and Laplace, who defined space as containing potentials that were space-time functions. The medium's physical character was itself ignored in favor of a continuous mathematical representation of a space in which each point was a function of spacetime coordinates. 11. For the modern view of physical fields, however, we should look to the 18th century work of Ruggiero Boscovich, 12 and the 19th century field theories of Michael Faraday and J. Clerk Maxwell. These three transformed the idea of a field from an auxiliary concept to be used for continuous matter, a concept chained to a mechanical carrier, to one of a potentially active energy pervading empty space, the region of continuous and vital forces. 13. Boscovich, an Italian mathematician, astronomer, and physicist, believed that action at a distance must take place through non-mechanical means. He therefore developed a theory of continuous force functions, which reduced matter to point particles in space and accounted for actions at a distance by forces of attraction and repulsion. In theory, all the quantitative properties of matter were basically dependent on the distance between particles and were a function of distance forces. 14. Michael Faraday, the brilliant English experimentalist and discoverer of electromagnetic induction, accepted the forces of Boscovich and believed them to constitute a medium in space. He tried to give substance to the force field itself and ended by reducing material masses to singular points in the field. Faraday considered atoms to be points surrounded by an atmosphere of forces, and he believed forces had properties such as hardness and solidity. Thus made up of atoms and forces, matter could act at a distance. More specifically, up to Faraday's time, Boscovich's followers had expressed electrical charges or magnetism mathematically as forces at a distance. Faraday introduced into this scheme the idea of lines, or tubes, of force surrounding magnets and having direction, as shown by iron filings, and qualities, push-pull, positive-negative. He envisaged such lines as traversing space through a medium, an ether, and explaining action at a distance. While others had thought in terms of magnet, iron, and distance, Faraday treated magnets and iron as insignificant parts in a total universal involvement. Important were the lines of force stretching out from the magnet in all directions like multitudinous atoms and spanning the universe. Where others had seen distance and action at a distance from material mass as centers of force, Faraday saw a medium and lines of force. Moreover, for Faraday these lines of force composed the representational scheme accounting for experimental results, and not an actual description of reality. They were theoretical constructs, not empirical concepts. J. Clerk Maxwell, the famous Scottish physicist who based much of his work on Faraday's, developed a mathematical theory of the electromagnetic field. He argued that light and magnetic energy travel in transverse waves and that light waves were electromagnetic in nature. He agreed with Faraday that between things exists an ether-like medium that carries the energy pervading space. Energy constitutes the substructure of electromagnetic fields and, like substance, is conserved. By this time the law of the conservation of energy was known. After mathematically combining electric and magnetic theories, Maxwell initially turned to mechanical models to explain electromagnetic force. At one time he considered such forces to be molecular vortices in the ether, whirling around at right angles to the lines of force. Eventually, however, Maxwell gave up mechanical models altogether and treated his lines of force as simple mathematical entities. His mathematical electromagnetic field theory gave energy a central role in natural philosophy and implied that reality was a total partnership between energy and matter. And in quantum terms, this is the accepted theory today. Basing his theory on Maxwell's electromagnetic field, Einstein also threw out the mechanical model of reality and replaced it with one mathematically combining both energy and matter and creating a continuity between them, E equals mc2. Gravitational fields, however, were omitted from electromagnetic field theory. This omission is significant, to say the least. Einstein tried, and others have continued the effort, to develop a unified field theory and relativity that would combine electric, electromagnetic, and gravitational fields, but without success. Gravitation is still a phenomenon of its own kind. Maxwell's field theory and subsequent elaboration by Einstein and others providing us with a new perspective on nature, ranking in importance with relativity and quantum theory as advances in our knowledge. Previously, natural laws were seen to operate on material bodies, through a material medium, and at that point where material changes or motion took place. Now all space was subject to laws, and laws that are essentially geometrical in form. Mechanics has thus been geometricized and geometry seen as materially active. Nature is fundamentally an electromagnetic field. What can we abstract about physical fields from this brief and compressed overview? First, considering the Boscovich-Faraday-Maxwell view as representing field theories, then a field is a condition of space surrounding a body, and not localized as are mechanical bodies. Second, this condition of space is the seat energy. Energy is thus continuously spread through space by a medium we call a field. Action at a distance then can be understood as action in a field. Third, field forces comprise the activation of this energy. The building block perspective on matter is but bricks with which objects were constructed was replaced by a view of matter as being active, composed of patterns of energy and excitation. Fourth, the field became a mathematical construct connecting observable events. It was not directly measurable and could not be directly proven empirically. Field cannot be operationally defined. 15 Confirmation of field theory is then based on the results to which it leads. Finally, and consequently, field forces are latent functions, or latent observables as they are known in Physics 16 as I will use the term here, Chapter 10. They are what underlie, as conditions, causes, or properties, the observed behavior of physical nature. I will eventually show that our intentional field has conceptual aspects similar to the physical fields of nature. 17 In this we will see that fields are not only fundamental to physical nature and its understanding, but also to humankind.